Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode is all about friction.
Yeah, friction!
Keeping things suspended up high thanks to friction, like this. And this. And even me.
Okay.
Climbing. Sliding. Lifting. And falling. Falling? I guess not yet. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and today we're talking about friction. I didn't slide.
Take two.
I can't, I'm still not. Oh, I know. I got it.
Take three.
Oh, socks don't work any better.
Take 15. 34. Take 36.
I don't know why I thought that would work.
Take 52.
I'm Phil, and today we're talking about friction! Sorry, okay. Oh, friction! We did it! We got it, everybody! How many takes was that? Oh. Well, still, we got it. Good work. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard. Well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. Check it out, I've improved the portal interface. Watch this. Yeah, and then I can scroll through experts, and oh, this is gonna be fun. And I've got my coordinates right there. Whoa. That's never happened. Okay. Hey, Sarah!
Hey, good to see you again.
Good to see you too, Sarah. From Mad Science, you're gonna help me max out friction!
Yeah, friction.
What do you think of my max out friction room?
It's amazing. It's so wonderful. So how are we gonna max out friction today?
In the lab, I had a ramp, and I had stuff with different surfaces on it.
Oh, that's so cool. It's too bad you don't have it here. We could totally test that out.
I can bring it here.
Awesome.
I have a new app on my phone that talks to the portal, and let's see. That's not what I... Oh, hold on. Okay, there we go, and... Whoa. Well, I can do this. It needs an update.
Yeah.
That's what the... Yeah!
There we go.
It is. Okay.
Perfect.
So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood and then we can try changing the bottom. I guess a block of wood isn't the right thing to use though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for
Are you
us.
sure you want to portal it in?
I'm sure. Just stand back
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring. It's pretty hard. This is my turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction! But we soon realized it'd be pretty hard to measure how much friction there was. You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
The case of the missing friction! It was rough all over in the big city. My toughest case yet, and I felt like I was getting nowhere. Someone stole all the city's friction. And it was my job to find out who and get it back. But after a week, I was no closer to solving the case. It was hard to get anything done now that there was no friction. Uptown to downtown, people were sliding all over with no way to stop themselves. It was chaos. Chaos, I tell you. But if there was any detective that could solve the case, it was me. But it's like my grandma always said, it's tough to follow leads if you can't sit in your chair. Nothing stays put in a city without friction. And you never appreciate something till it's gone. The phone rang. Sure, I wanted to answer it, but it slipped through my grasp just like this case. The mayor was on the line. He wanted to know if I'd made any progress. But I felt I was going in circles.
I'm gonna have to call you back, Mr. Mayor.
Without friction, you couldn't do very much at all. It was going to be my toughest case yet. Sounds good. Sarah and I are maxing out a friction ramp. Step 1, make a giant ramp. There, are we done?
Great, I think so.
We're done. But it proved a bit hard to lift up to the second floor. Fortunately, Sarah had an idea.
Maybe we could use this crane.
We use the crane! Oh, yeah, I've got a 5-ton crane at Science Max headquarters. Good thinking, Sarah. So we rigged it up and tried it out. The bonus was we could make the ramp any angle we wanted. Okay, time to get my helmet, because don't go any higher than that, because I don't have my helmet. And then we will start sliding down.
All
Friction
right,
ramp!
friction.
I got on the slide, and Sarah lifted it up until I started moving. Ah! And that allowed us to record our results.
We're at 2 meters.
2 meters! Recorded! First recording done,
All
now we
right.
switched it up. We tried it again with Sarah on the slide to see if she slid at the same height. And she did.
Yeah.
Now we have a way to record the results. The plastic sled went down the ramp at this height. Things with more friction will mean the mark is higher, and less friction will mean the mark is lower. So then, we tried it with cardboard! Cardboard! What did we get? And it was?
A little over 2 meters.
Meaning? Cardboard is a little bit less slippy than the plastic of the sled.
All right.
Ready for carpet sled?
Good to go.
Here we go. Oh, past 2 meters. Oh, almost 3.
Here we go.
carpet had even more.
Oh my gosh, we're going this side.
Whoa!
That was so cool.
That was exactly 3.
Then we tried foam.
Coming up on 2 meters. All right, coming up to 3. It won't go up any higher.
And just like the wood block, the foam didn't slide at all.
What if I like do this and then I slide? Right, so, friction sled on foam, highest friction of all of the materials. Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take 2 books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. 2 books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then. Science! That was close.
Sarah and I have used our maxed out friction ramp and compared the regular sled to cardboard and foam. What's next?
We've waxed the bottom of this sled, and we're gonna try a wax sled next.
Wax sled!
All right, here we go. Right.
1 meter.
Oh boy.
1.5 meters.
Whoa!
Wax sled! Woo! The slipperiest yet. Only 1.5 meters.
That's awesome. Do you have anything that's more slippery?
Yeah, we do. We have ice sled. Are you ready to try it out?
So ready to try it out.
Okay, let's do it.
All right.
And
There we go. Whoa! That was awesome.
look how far you went.
That was so cool.
And only 1.25 meters.
Least amount of friction.
Ice wins. So I think we should do something else to max this out, though.
Maybe bringing it up a little bit more and
Yeah.
using something with less friction.
Wait, I have an idea. Yeah, okay, come with me. This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws. The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction. Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction, but there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it, all thanks to friction. So now, let's max it out. This is a super maxed out climbing frog. Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch. And it does work. It's just a lot harder to pull on the ropes, but it totally works. Whoa, careful, whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I can just fit. Newton's first law in 60 seconds. Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go. Sarah and I have recorded a lot of results on our ramp by raising it till we started to slide.
Here we go.
Now we've decided to raise the ramp to the highest point and see how far we can go using some low friction things, like a wheeled cart. I've made a double bike cart. Wheels are great for moving. They have rolling friction, right? Which is different from sliding friction. What happened?
You went through all those those boxes back there.
That was it. We went really far. Total fun. Let's try something else.
So what are we gonna do next?
Now we're gonna do the frictionless thing that we have at Science Max headquarters, a hover disc.
Oh my gosh, that's so cool. Where did you get it?
Built it, season 1.
Amazing.
As you may remember from that episode, a hover disc uses air to greatly reduce the friction with the ground.
Here we go.
So what would a hover disc do on a ramp?
Right.
Only one way to find out. Whoa! That was amazing!
That was awesome.
So let's recap. Friction is when two surfaces rub against each other. You can have a very small amount of friction or a very large amount, depending on the materials. And using science to reduce friction results in the best sledding experiences. Nicely done. Science Max, experiments at large. Your turn?
My turn? Yeah, let's
Okay,
do
so
it.
take those, and I'll get this, and then I'll give you the helmet. And then we gotta rebuild rebuilding the boxes is like the hardest part of this
Yeah.
whole situation, but. No, I should. Everything's fine. And then this one, and then that one, and then that one, and there you go. Aha! Giant climbing frog! Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today on Science Max, it's all about the power of water. I'll see you later. We filter it, pump it, paint with it, and most importantly, use it to crush stuff. Crushing! All on this episode of Science Max, experiments at large. Ha. Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need. First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store. Here's how you build your own hydraulically powered arm. First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together. Because we are holding this whole thing together with elastics. Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe. Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over that way. Oh, Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go. Come on.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat. But this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes,
Yeah, because we
yes.
got some cool stuff planned. Okay, so we're just gonna get the table in here. Oh, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We can make it bigger, we can make
What
it
if we did
arm.
it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
A force, I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we can do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small...
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No! My cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Right, I am. Wait, hold on, I will remake the crackers into, see, look, see, it's fine. It's fine, I'm not really gonna eat that, I'm just kidding.
Chris and I are maxing out our hydraulic crusher.
Yes, yes. Before we get to that, I have a little game I want to play.
Okay, great.
Okay. You can pick either the small one.
The big
or
one!
Okay.
So what's the game?
Simple thumb war. I'm gonna press down this side. You press down that side. We'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go! Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go! Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go.
Ooh, how about an orange? 1, 2, 3.
We squeeze down and... Then we tried a walnut.
Are you allergic to nuts?
I am not.
1, 2, 3.
When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do.
We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we
we can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal.
Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a
gravel, sand, and charcoal filter.
The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water.
Delicious. Science.
Max Historica. This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw, which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right, used to make holes in water.
What? No! Look, did you even do your homework?
Hold on, it's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just just sit down. And I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut,
It's cracking. Oh, there we go. Oh, it's gonna leak.
and then a can of pop. Science Max Cola, now in the new, smaller can.
Let's really challenge this press. Perfect.
A piece of wood. We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping. Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern. Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet. If you put tape on what you're painting, you can remove it later to make parts that aren't painted. Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants. Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad. Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table. To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with a little happy town. This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings. I'll see you later. I'm gonna take a swim in the river now. There are lots of ways to experiment. Change the amount of water, or the steepness of the angle. Look at the soil, it's all getting eroded over here. Or the way the town is laid out. Every time you do it, the river goes in a different direction. And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
And that is the power of water. Chris and I are maxing out a hydraulic crushing machine. What about this? Is this what we're gonna use? We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab. Oh, this is good. Oh, look at that! Oh, is this what we're using?
No.
Oh, I can use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it. This is it.
All right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. Okay. We started out with the piece of wood which defeated our last press. And go! Awesome. Reversing. It turned our wood into a pancake. Whoa, totally flattened. So it was time to try some other stuff. We crushed a ball of plasticine. That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball. Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind. This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press. This is a metal vise, hard, strong,
Yeah, steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally exploded. Science Max, experiments at large, hydraulics. Whoa. Nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse. Huh? Wait a minute, I didn't think this through.
Do you have anything?
I have a coconut. I'm supposed to take the paprika burger. And there you go. Perfectly clean filtered water. One cheese and cracker soup. Okay.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, experiments at large. Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to
blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxodrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Better late than never, it's the procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right.
And last but not least, the regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built, and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind this small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law.
no, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later. We're not
opposite
doing this bit now. We're doing that bit in a minute, so we can. No, I said we're doing it later. We're doing it later. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock car?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah?
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
You did.
You did let it go.
I just let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay, balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tanks, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity, he gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart. This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? weird. Just don't eat it. Now, it's time to max it out.
I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool and I realized I should have duct taped the pocket because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back. When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction. Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's third... No, hold on. Newton's third law. Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right. So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use two balls. I swing two balls up, and two balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls, bowling balls, instead of smaller balls. And I think it's gonna work the same way. Let's find out. You throw one out, and haha, yeah, it works the same. Okay, now let's try it with two balls. Okay, ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh. Ah!
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube,
Yeah.
and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks, Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go that
forward.
way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Yeah! Woo! Uh-oh. Woo-hoo-hoo. That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Wait, I can play Mary Had a Little Lamb. It's working! It's working! Newton's cradle out of bowling balls. Come on! You know this one, sing along. Whee! Come on! I mean, come on! Science!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
My name is Phil,
And I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
This episode of Science Max is all about earthquakes.
Exciting.
How do we build something that won't fall apart when shaken? Plus a lot of other ways to shake things or build things.
Science!
All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when two plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... Two books, 4 elastic bands, and four rubber balls. Oh, wait. Okay. Four rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put one set on one side, one set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books in the middle-ish area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do.
You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books.
And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Whoa. And there it goes. And when you've done that, what you do is you be a Science Maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there, and then we shake it, and we see what happens. Oh no! Oh, there it goes. So that is what we're going to be doing today on Science Max Experiments at Large. We're going to be making a giant shaker table and putting a giant structure on top and seeing how we design it to make sure it stands up to the shaking of an earthquake. I'm gonna need an expert to help me though. Oh, I know, Anne would be really good at this. Okay, all I need to do is get Anne and we can start. Oh, come on. There it is. All right.
Hey, Anne, I feel weird. Why do I feel weird?
I think you're a chair.
Well, that's not good. Hold on a second.
Am I good? Okay.
Hi, Anne. Good to see you. Here's your lab coat.
Thank you.
So you're from Let's Talk Science, right?
I am.
All about science education, just like us. Today, I need your help to max out our earthquake table. This is the table
This looks
part,
great.
obviously, but this is a tower I've made out of popsicle sticks. So in order to max it out, I've already built a large shaker table. Come on. This is my large shaker table.
So it's got basketballs underneath as the 4 balls, but it works exactly the same.
Whoa. Okay, so what kind of tower should we make for the shaker table?
If we want something tall, then we'll reinforce it a couple spots. But the true test, it's got to have some sort of weight on top so that it will mimic the weight that would be on a real tower.
Right, so maybe I could get a plastic bin and I'll just put some sandbags for weight inside.
That would be perfect.
And then balls, so that when it falls over, the balls will go everywhere.
That would be perfect.
Okay, great. Shake off. I don't know. I think we should just get off.
Another thing that happens during an earthquake is soil liquefaction. Liquefaction means something turns to liquid. In this case, the very ground you might be standing on. Here's how you can experiment with soil liquefaction. All you need is a plastic container and some water, not very much, barely enough to cover the bottom of the container, because what you're gonna put in next is sand. And you wanna put it in there and spread it around. Just add enough sand so it just starts to turn dry on the very last layer. So here is a house that I'm going to put on top. And now I will simulate an earthquake. The water rises up and it sort of turns to liquid. Soil liquefaction. And heavy things like houses and cars, they tend to sink like that. And then the soil rehardens and everybody's houses are stuck in the mud. Now, let's max it out. This is a giant tub of sand and water, and this is a vibrating platform that will simulate an earthquake. Now, as you can see, this sand is totally solid. I can jump all around on this sand, no problem. But when I turn on the vibrating table and simulate an earthquake, things will change.
The vibrations bring the water below the sand to the surface and cause the sand particles to separate. What was solid now turns to liquid in my simulated earthquake, and I start to sink.
I'm up to my shins! And there you go, soil liquefaction. Hey, look at that. It's totally solid. Woo-hoo-hoo! Soil liquefaction! I'm totally... Uh-oh. You know what I realized? When it stops vibrating, it really becomes solid again. And it's very tough to... Well, there you go. Soil liquefaction. I'm really kind of stuck in here.
So Anne and I have made a large shaker table. Now it's just a matter of designing a building. We use lumber and cut it up, use screws to attach it all together, put a platform on top for a weight, and attach it securely to our shaker table. The building is super simple, just 4 corners and a few planks around the outside. No structure in the middle. And finally, the big heavy weight on the top.
There.
We attach a pole to the shaker table so we can shake from a safe distance and try it out.
Okay, very slow.
Forward.
Let's see how much shaking it can stand with our shakeometer.
That seems to be okay.
Kidding.
Oh no.
We barely start to shake our tower before it collapses.
Oh, that didn't really last very long, did it?
It completely folded up on itself. What do we do to fix this, make it better?
I think the easiest thing we can do is to use thicker wood. It'll make it less wobbly.
Okay, sure, let's make another one. High fives. We do have lots of wood, that's a good thing.
Anne and I are trying small improvements every time.
There.
Our last building used thinner pieces of wood. Now we're using thicker wood, which we think will help keep the weight at the top from collapsing the building. Everything else about the design of our building is the same. We put the weight on top and fix our pole, and we're good to go.
All right, you ready?
Okay. starting to creak.
But it recovers. You can see it lean, and then it comes back, and it resets.
Definitely doing better than the last one.
Oh no.
I'm impressed.
Uh-oh, here we go.
But it definitely did better than the first one.
It did better than the first one.
And the thicker wood definitely helped.
But it was really starting to turn.
I think on the next one, we need some platforms in the center to help strengthen it even more.
Earthquake Building 3.0. Thicker wood this time, but with platforms in the middle.
So we're gonna see how well this version works with these middle parts that'll hopefully reinforce.
And they're just like the floors of a building.
Okay, well, let's find out if it's gonna make any difference.
Starting to wobble a little, but it looks pretty good.
As soon as we start shaking, it's really obvious this building is more solid.
Uh-oh, starting to creak. Oh, it's really starting to creak.
The platforms in the middle really seem to improve the structure. You can see it bend all the way over and still recover. But still, it wasn't long before...
Really starting to lean.
Wow, the extra pieces really kind of made it more impressive.
It definitely lasted a lot longer than the other two.
It did, but here's what I'm wondering. Are we going in the wrong direction?
What do you mean?
Well, because if it's really solid, it resists the change.
Okay, I see where you're going with this.
So if we make it flexible, it can resist the shaking of an earthquake.
I think it's worth a shot.
Yeah, okay, let's do it.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. My tuna fish and meatball sub soup is coming along quite nicely. But what will we have for dessert? I know. How about earthquake buildings? Ha ha! It's a building made out of wafer cookies. But the people on Vanilla Street built in the gelatin neighborhood. And the people on Chocolate Street built in the crispy rice part of town. Exciting. Now, here comes the earthquake. Oh no! Oh, it's shaking! Oh, the shaking is come and gone for the people on Chocolate Avenue, and their building is still standing. Now, let's take a look over here on Vanilla Street, and here comes an earthquake. Oh no! Oh dear! Looks like the people on Vanilla Street are going to have to rebuild their building because it's all fallen over and being eaten. Delicious. Buildings can be built the same way, but the kind of soil they sit on make a large difference if there's an earthquake. Shaky, wiggly soil or solid, non-moving soil. So there you go, an experiment you can try at home. Delicious. Well, I'm Buster Beaker, and thank you for joining me on this episode of Cooking with Science. Now to try my soup.
Seismometer in 60 seconds!
Learning how to predict and measure earthquakes is an important branch of science. The Earth is shaking, but which way did the earthquake come from? It's all about measuring the vibrations, and to do that, you need a seismometer. All you need is a ball, some paper cups, some modeling clay, a pencil, and science tape, which is the same thing as invisible tape, except I use this tape for science. First, take your pencil and stick it straight down into the modeling clay. Then, you take your cups and you arrange them in a circle and tape the cups down. And that goes right in the middle, just like that. Now what you do is you take the ball and you carefully balance it on the pencil. Now you have created a seismometer. It will tell you what direction an earthquake came from. Watch, I will be the earthquake. Ready? Did you see that? The ball fell into the cup facing the direction that I hit the table. And now I'm gonna hit the table from over here. Yep, it fell in the direction that I hit the table. Okay, let's try from over here. There you go, your very own seismometer that you can use to measure earthquakes that you create on the table.
Back to our earthquake building. Ann and I tried a few different designs, and they each got a little better. But now we're wondering what would happen if we built the tower out of very flexible material. We used some plastic tubing and attached the wood with bungee cords, which are like big elastics.
Wow, okay, so looks good.
So let's test it.
Okay.
And sure enough, when we start shaking it, the tower holds up to as much shaking as we can give it.
Wait,
What?
aren't we missing something?
Oh, yeah, we're missing the weight at the top. Of course.
So I think we need to try it again.
So we add the weight to the top, and then everything changes.
Oh, no.
Look at it twist.
Oh, dear.
It's twisted.
A flexible tower is great until you try to put a weight at the top. And then it just seems really unstable.
Oh, look at that. It's totally bent.
It didn't break at all, it just fell over.
Yeah, it couldn't even support the weight.
So it was almost too flexible.
So I guess we should go back to a more rigid design. But what if we change the shape a little bit? 'Cause you know what I was thinking? This is a very stable shape. Triangle, because triangles are really strong. What about we make an X?
Like a triangle within a triangle.
Triangle, and then triangle. So that really reinforces all of the shaking, like all of the motion.
We'll never know until we try.
All right. Uh-oh. I have all my friends coming over, and I don't have a table. But that's okay. I will make a table using my friends. This is an awesome experiment you can do with 4 friends. Come on in, science friends. I've got Sam and Dylan and Polly here to help me. So everybody turn to your left and sit sideways on the chair, and then scooch the chairs into the middle. And then everybody leans back onto the knees of the other person. And then, this is why I said you need 4 friends, because you need the 5th person to remove the chairs. Whoa. The reason why this works is because everybody's weight is being supported on the legs of the person next to them. Okay, we're gonna rotate in a circle, everybody. Okay, ready? Here we go, rotating, rotating. Oh, science table. Ooh, hey, we're pretty good at this. Okay, uh-oh. Oh no, oh no! So there you go. Awesome way to make a table using your friends. Well done, science. Here's an experiment you can do to impress the adults in your house. You need 3 glasses, all of equal height, and 3 knives, not sharp knives, the dull knives you use, maybe the ones you use at dinner time. Take your 3 knives and put them in a triangle, all equally spaced out. Then move the knives together to make a little triangle, right like that. Then what you want to do is you want to carefully arrange the knives so each knife is going above one knife and below another knife. So there we go. Then you want to take this careful pattern that you created and you want to put it on top of your 3 glasses. One where each handle of the knives are going to be. And if you place it carefully and you've done the over-unders correctly, it will stay up. Pretty amazing. The knives support their own weight. But they don't just support their own weight, they can support a lot more weight too. Pretty amazing, right? This is a great experiment. It's also something really interesting that we can max out. Come on. And here you go, the maxed out knife balance. I've got 3 pieces of lumber and 3 barrels, and as you can see, the pattern is exactly the same. Under, over, under, over, under, over. Ha-ha. So, the question is, how much faith do I have in science? It totally supports my weight. I know it's going to work because I know that a 2x4, which is the kind of lumber I'm using, can hold up my weight. So that means the structure can support me. Science! You know what the cool thing is? The cool thing is that even though it's holding me up, each one of these pieces of wood is only up because it's supported by the others. You pull one out and it all falls apart.
Ann and I have tried solid towers and flexible towers, and nothing has worked fantastically yet with a big weight on the top. Having a big weight on the top of our tower means we need something that will resist the movement of that weight. So now we're going to start with a triangle. Unlike a rectangle, triangles are very stable.
A wider base keeps the structure from swaying too much. And cross braces in the middle mean that there are other triangles within our triangle, all the better to resist movement.
Thank you.
After Ann and I built our tower, we added the weight to the top, secured it to the base, and tried it out.
Okay, here we go.
Looking good.
No problem.
Not twisting.
It's
Not leaning.
not even creaking.
No, it looks really good.
Wow, this one is really solid. As you can see, this tower is way more solid than our square tower or the flexible tower.
Okay, look at that. Like, if that's not an earthquake, I don't know what is. Look at that. Look at the way the ground is moving.
I don't know if we can shake it much more than this.
Faster. Our triangular tower is up past a level of shaking that made the other towers collapse. Now it's time to max out the shaking.
There's only one level of shaking that we can do above this.
What's that?
We shake from either side.
We give it all we have. The floor was bouncing from side to side, the tower was tilting, and was totally solid.
It's still holding strong.
In fact, Ann and I wore out before the building showed any signs of falling over.
I think we've done it.
Nice job.
Nice! Science Max Experiments at Large earthquake-proof building. I mean, come on. That was impressive.
I like it.
Here is an invisible tower. Huh? I escaped.
I'm just preparing I forgot my line. Hello. Just gonna add some more salt to the soup. Delicious.
Well, humans have been figuring out ways to figure out just that. I said figure out twice. I'm gonna start again. Okay.
English is not my first language.
I guess those are staying in there.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about vibration and frequency. Frequency and vibration. What's the difference? We build a maxed out vibrobot, spin a giant disc, suspend water, and play with lasers. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites, and welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max Experiments at Large, we're going to be looking at vibration. Vibration is when things go back and forth, and back and forth. All kinds of things vibrate, like pendulums. Pendulums. Wait, and pendulum. Pendulums are designed to swing back and forth. Stop that. Also, metronomes. Metronomes are used by people when they're practicing music to keep accurate time. Yeah. Okay, putting it back. And okay. We're gonna be building. Whoa, okay. We're gonna be building this little guy. This is a vibrobot, and he vibrates and he skitters around on the paper. And if we take the caps off the markers, he makes interesting patterns on the paper. Okay, so let's get started. Let's build a vibrobot. Okay. Oh yeah, you know what? Maybe it's time to take off the ski boots, huh? Whew. There we go, that's better. So today, like I said, we're gonna be making a vibrobot. And here are all the materials you need to make your own. Plastic cup, 3 markers, an electric motor, just make sure you ask an adult first, a battery, a plastic drink bottle cap, a toothpick, scissors. This kind of tape is called electrical tape. Science tape, which is the same as invisible tape, but of course I use this tape only for science. And some modeling clay. And these are 2 bendy straws that I've taped googly eyes to. These are not necessary. I just like them for decoration. Now remember, if I'm going too fast here, which I probably will be, you can get all of the steps on how to make your very own VibroBot on our website. Okay, so here's how you get started. First, you're gonna make the feet for your VibroBot. So I attach some science tape to the markers, and then I put the marker on the bottom of the cup. And then I do that again to the next marker, and then the third, balance it like that. There. Next thing you wanna do is take your plastic drink bottle cap and make a hole with a toothpick. You wanna make it off to the side, right about there. Just like that. That's so when it turns, it will be off center. That's what's gonna give us our vibration. So once you've made that hole, take some modeling clay and stick it in the cap to give it some weight. When you've done that, stick it onto the shaft of your motor like this. See how it's off center there? Now we just need to attach it to the VibroBot. I just put it right here on the top, and I like to attach the battery to the back of the cup. And now, finally, we're going to attach the eyes. We take some science tape, and we put the straws over here. I am VibroBot. I am here to vibrate. Take me to your leader. So then, you attach your tape with the wire to the top of the battery there, and then the other wire to the bottom of the battery. Just like that, and let your VibroBot make some art. Ha 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 ha. Now, if the battery is new, your VibroBot might be jumping up and down quite a bit. So you can do what I like to do and add some more weight, and then you make better lines with your VibroBot. And your VibroBot makes art. How long will he last? Probably till lunch. And there you go. VibroBot art! Art made by a robot. How cool is that? So that's what we're gonna do today. I'm gonna meet Chris from Logix Academy, and he's gonna help me max out the VibroBot. Plus, we're gonna learn a little bit more about vibration. Come on. Oh, hey, Chris.
Oh, hey, Phil.
Thanks for coming.
My pleasure.
Okay, here's your Science Max lab coat.
Thank you.
So you guys at Logix Academy, you also build a VibroBot, right?
That's right, we do.
This is mine, and it works pretty well.
That's awesome.
So, I want to max this out.
Cool.
So I thought we would start with, instead of this motor, we would start with this motor.
Wow.
It used to be a round circle, but I cut it off so that it's off center.
Perfect.
I've also got, this is our battery.
Fantastic.
That's as far as I've gotten so far.
Well, it looks like we need a frame next.
Right, something to be the cup.
That's right.
So we just need some sort of larger cup.
Ooh, how about that metal shelf over there?
Oh, this thing?
Yeah.
This is just something I keep my parts on.
It's perfect.
Really?
Yep, the shelves will house everything that we need, and it looks like it'll be strong enough to hold everything together.
Now, the VibroBot had markers on the bottom of it.
That's right.
To make a little pattern. Should we try that with this?
Because we're going bigger, what if we used paint and paintbrushes instead?
Okay, sure. We could attach paintbrushes to the legs. Pass me one. All right, so now all we need to do is get some paint and some paper.
That's right.
And we can fire it up. Okay, let's move it over this way.
Vibration and frequency. What's the difference? They're all connected. Ta-da! Now, whoa. Vibration is things going back and forth. Back and forth. And back and forth. It's a cycle. Cycle, 25 bucks. Oh yeah, it's the wrong kind of cycle. Never mind. Well, if that's vibration, then what's frequency? Well, frequency is a measure of how fast or slow, how frequent those vibrations happen. Look at this bowling ball. Look. It is swinging back and forth, but not very fast. You could say it has a low frequency. We measure all kinds of things by the frequency. This thing is terrifying. When you turn the dial on your radio, you're tuning in to different frequencies of radio waves. Hey, look at this punching balloon. It's going very fast. You could say it has a high frequency. So,
now you know. Vibration is something going back and forth, and frequency is how quickly it does it. Ramona, the bowling ball keeps coming through everything. How do you turn it off?
Okay, back to our main experiment. Chris and I are taking a vibrobot and maxing it out. We have a large motor and a battery, and we're taping it all to some shelving. Just like our small vibrobot, our motor needs something to make it unbalanced when it spins. That's what will cause the vibrations.
It's just taped. I haven't attached it in any other way. Do you think that's okay?
As an engineer, I have superior faith in duct tape.
Okay, well, that's good to know.
We're also adding an on-off switch and some paintbrushes on the bottoms of the legs so our maxed out vibrobot can make art just like the small one. The final step, dipping the brushes in paint and setting it on a big piece of paper. We fire it up and it immediately shakes everything off the shelves.
It totally spilled all the stuff on the shelves.
The motor shakes the vibrobot a lot. But there's a problem. All that shaking is starting to take its toll on the shelves. The wheels come off, the screws come out, and finally...
Whoa. It totally shook itself apart.
Destroyed itself.
The shelving unit just completely falls apart when it's being shaken.
Vibration is really hard on the structure of an object. We need something more sturdy, something that can take weight.
Steps, maybe?
Yeah.
Okay, hold on.
Okay.
Okay.
Yeah, this looks much better.
Okay, great. So we build the new vibrobot out of this. So more paintbrushes,
Bigger motor, more paint,
more everything.
more everything.
All right, good.
This is a pendulum. It's just a weight suspended on a line and anchored from above. Pretty simple. Pendulums were used for hundreds of years for all kinds of reasons, but most famously in clocks. Why were pendulums used in clocks? Well, here's why. Let's mark every time the pendulum hits the bottom of the swing, right here. Okay, watch. All right, now here's the question. How fast will the beeps be if I swing it from much higher up? Let's find out.
No matter how high the pendulum swings, it keeps the same frequency. That's why they were used in clocks, because it could swing for a long while, and even though it would lose energy, it would still keep perfect time. The frequency of a pendulum doesn't change, no matter how high it swings or how much weight is on the bottom. The frequency comes from how long the line is.
Now this is a pendulum wave.
Because each bowling ball has a line that's a different length, they have a slightly different frequency. They start out swinging together, but soon they start to make interesting patterns. Remember, each pendulum is keeping its own perfect time, even if it's slowing down. It's only the length of the line that gives each pendulum a different frequency.
And now we're gonna max it out with well, I guess these are already bowling balls, so this is already pretty maxed out. I'm just gonna leave that there. These are balloons. This is a laser, and these are awesome laser safety glasses. Now, lasers are made of light, and light has a frequency. In fact, each color of light has a different frequency. This is a red laser. Check it out. Yeah, cool. This is also a very powerful laser. Oh, I can pop the blue balloon with the red laser because the blue absorbed the red light from the laser and then it heated up and the balloon popped. But here's the cool thing. I cannot pop a red balloon with a red laser because the red balloon reflects the red light from the red laser and I can't pop it. If I wanted to pop a balloon with a red laser, I need to use a darker balloon, one that absorbs the red light, like a black balloon. Haha. So there you go. Lasers, frequencies of light. I'm gonna keep this red balloon because it's always nice to have a balloon.
Chris and I are maxing out the vibrobot.
But our last version shook itself apart. Now the plan is to start with something more solid and try again. We found some very solid steps and added an even bigger motor, an even bigger battery, and attached a half-circle wheel to make the vibrations when the motor spins. We add some paintbrushes and fire it up.
Here we go! Come on!
Go, Vibrobot!
It wants to move.
Is it moving at all? So it's still not working. It's sort of getting caught in the paper and it's on the paintbrushes.
And the paintbrushes seem to be absorbing too much vibration, and then the paper's stopping it as well.
So why don't we remove the paintbrushes?
Yeah.
And we might as well remove the paper if we don't have any more paintbrushes.
Yes.
And we'll see what happens.
We'll see what happens.
Okay. No paintbrushes, no paper.
Okay.
Now let's try it. 3, 2, 1, go!
Yeah! Aha! It's moving. Not bad.
The shaking is good, but I don't know if the shaking is enough. So what do we do?
Well, we could add another battery.
Another battery which would give it more power?
That's right.
Okay, let's try that.
Okay.
Okay, so it wasn't working before.
No.
Not enough power. And now we've got a second battery here.
That's right. We've wired them up so that one power feeds into the other, so we've got twice as much juice as we did.
So it's just a matter of clipping this onto there.
That's right, but hold on.
Yeah, safety glasses, because now we don't know what's going to happen anymore. Ready? 3, 2, 1. The extra battery makes a big difference. The new Vibrobot shakes around and only shakes itself apart a little. All right, that was amazing. Okay, so all we needed was more power.
That's right. I think it didn't have enough power to vibrate up and down, and that's why it wasn't moving every time it hit the ground.
So I think if we're gonna use this much power, I think we need to build it again.
Okay.
Build it even stronger and with a bigger motor.
Yeah?
And more power. And then maybe I ride it. Do you think we can build that?
Of course.
Of course. Okay, let's do it. You want to see something cool? I can make this water levitate, defy gravity using the power of science. You want to see? Behold! Gravity-defying water! I can even make the water go very slowly. Or I can make the water go back up into the hose. Or I can make the water completely stop. You know what's interesting? The water does not seem to be stopped for me. You see stopped water because you are looking at it through a TV camera. See? Real life, TV camera. Real life, TV camera. You see, movie cameras and TV cameras take a whole bunch of still photos and then run them together really, really fast. 24 times a second for our TV cameras. I have created a device that drops water at 24 times a second, and what happens is everything lines up. So it looks like the water drops aren't moving. But watch this. I grab the hose and it's fine. But I let it go, and the hose is vibrating back and forth at exactly the same time the camera shutter is going back and forth, and everything looks like it's stopped. The power of frequency has defied gravity. Okay, so not really. It's kind of a camera trick, but I prefer to call it science. Here's a fun way to play with things going back and forth. This is Euler's disc, and it's designed to spin like this. What's going on is friction and gravity are slowing that down and pulling it towards the Earth. Now, you don't need a fancy disc like this to do this at home. All you need is a pot lid. Check it out. When the pot lid spins, friction and gravity start to slow it down, which means each spin gets lower and lower, and the frequency gets higher and higher. But the difference between a pot lid and Euler's disc is Euler's disc is made to go for as long as possible. The heavy puck has a slightly rounded edge and sits on a glass surface that is slightly concave, like a bowl. All of this is designed to make Euler's disc last a really long time, which is quite a while. But eventually, friction and gravity pull the disc down, and finally, it stops.
Pretty amazing, right?
Well, wait till we max it out.
This is Trevor, head of the Science Max build team.
Hey.
Thanks for setting this up, Trevor. So what is this?
This is a giant side of a spool, big hydro spool.
Okay, so this is the largest disc that we could totally find, and we've got it all hooked up here. We lift it up, we spin it, and then you pull the thing and it will drop down and spin like a coin, because it's the only way we can do that with something this heavy.
Yeah.
Ready?
I'm ready.
Okay.
Trevor and I hoist it up and get it suspended above the ground. Then I start to wind it up.
Ready?
When it's going fast enough,
And go, Trevor!
Trevor pulls the release and it turns out a 200-kilogram spinning disc works exactly the same. As it spins and rolls, gravity and friction work on it, and the frequency speeds up as it gets closer to the ground until it stops.
Giant Oilers disc. Nicely done, Trevor.
That was awesome.
That was great. Let's do it again.
All right.
Our Vibrobot was working well, so that means it's time to make it way bigger. We started with a big metal table and added a huge motor, one 20 times as powerful as the last one. Instead of batteries giving us 12 volts of power, we're going to use a plug, which is 10 times more power. We've added an off-center wheel for vibration, bolted the motor to the frame, and added a protective cage all around to prevent anything from flying off. It even has a seat for me to ride.
Okay.
Okay.
You ready?
Ready?
Here we
We
go.
fire it up and it's very shaky.
Oh, wow. Wow. That was really uncomfortable. It was like very bangy, even with the seat.
Yeah.
I'm gonna try standing on
All
it.
right.
When I try standing on it, the Vibrobot lives up to its name. It vibrates all around the lab.
Oh, wow. My legs are numb to the knee.
I'm not surprised.
Vibrobot!
All right.
Yeah, that worked really well.
That was awesome.
I really can't feel my feet right now. And it held together, which is impressive.
That's right. The more power and the stronger structure paid off.
Yeah, the only thing I regret is not getting a chance to, wait a minute, come with me. Okay, so I achieved my dream of riding the Vibrobot.
You did.
But we never got a chance to make art, so we've dipped a whole bunch of nuts and bolts and heavy things in paint.
Yep.
And now we're gonna turn on the Vibrobot and see if we can make some art. Let's see how it looks.
Oh, wow.
Ta-da! Vibrobot art. Vibrobot has been a huge success, and we've got some art to keep. High fives. Well done. Science Max, experiments at large. Who gets to keep the art?
Rock, paper, scissors.
Okay. 1, 2, 3. Okay, tie. 1, 2, 3. Tie. 1, 2, 3. 1, 2, 3. Wow. 1, 2, 3. Ah, tie. 1, 2, 3. Man. There's gonna be a red balloon, but those red balloons are gonna be pushing this way. And then this afternoon, we're gonna have this blue balloon, which is quite nice. Over to you, Kathy. Thanks, Kathy. Science! I figured we would have maybe a bigger motor.
Yes.
Or a bigger, no. I'm gonna try that again. All thrusters ahead. Whoa! Balloons. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode is all about chemical reactions.
Nom nom nom. Nom nom nom. Nom 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 nom. Nom nom delicious.
Reactions to make things fly, to make things glow, to make things pop, and to make things fly.
That worked.
Wait, did I mention the flying? I'm sure I did, but I'm mentioning it again because it's awesome. All on this episode of Science Max, Experiments at Large.
Okay, Science Maximites, prepare to hurtle through the cosmos. I am Captain Phil, and today we're going to be building rockets on Science Max. Now, we've built rockets before, like this one, powered by air pressure. And this one, stomp rockets, which were also technically powered by air pressure. Air pressure rocket! But today, Science Maximites, we are going to be building rockets powered by chemical powers. Away! Okay, I promise it'll be more exciting than that. Because today, Science Maximites, we are going to be looking at chemistry. Chemistry is when two molecules combine to make another molecule. Like magic, ooh. So let's take a look at what will be powering our chemical rocket. This, it's an antacid tablet. When you put an antacid tablet in water, it makes little bubbles of carbon dioxide gas. This happens because of a reaction between two kinds of molecules called acids and bases. Like vinegar and baking soda, but all contained in a small package that won't start working until you put it in water. If we contain the reaction, the carbon dioxide gas builds up and creates pressure. High five for science. All right, so let's look at our chemical-powered rocket. What you need is one of these. This is a film canister. And ask your parents what that actually means because they're not used for holding film anymore. You can get these at craft stores, though, to hold paint or little things. But really, all you need is a plastic container with a good lid that snaps on nice and tight and keeps the air in. And then, of course, what you need are your antacid tablets and a little bit of water. So pour in some water and then put in your antacid tablet and snap the lid on. Flip it over and wait for the carbon dioxide gas to build up, which will build up pressure, which will launch your rocket. Ha-ha! So there you go, a chemical-powered rocket. Come on, let's max it out. So first, I need an expert to help me. Lisa from Logix Academy, of course. Logix Academy people have helped me launch all the rockets on Science Max. This is gonna be great. I'm gonna get my helmet first. Okay, let's launch some rockets! Let's go! Whoa, wow, it's really dark in this room. I can't see anything.
Bill?
Lisa?
Bill?
Lisa? What?
Bill?
Where did this come from? I guess the portal's malfunctioning. Hey, Lisa!
Hi!
From Logix Academy, great to have you here.
Great to be here.
Let's put this over there. We are here to max out the chemistry rocket!
Ooh, what is that?
It's just a small plastic container. But when we put an antacid tablet in there and some water,
We get a chemical reaction.
we get a chemical reaction. And so that's what creates the pressure. And then that pops the lid off and we get a little rocket.
Kaboom!
But now we're going to max it out. Get a bigger container and more...
Wait.
What?
How about if we launch a whole bunch of them?
Ooh, so we just get a lot of the small one and we launch them all at the same time.
Exactly.
Okay, great. So we just need a whole bunch of these and a whole bunch of...
And a whole bunch of science antacid.
Yeah, well, that's okay. I get them both in bulk. Come on, let's go put it together. I'm an acid, and I'm a base, and we are enemies. Whoa, Well, we're not really enemies. Yeah, that's true. It's all about how we react chemically. You see, as an acid, I really want to give protons away. Protons? Who needs your protons? Get your protons here. Protons, I got more than I want. I don't need them anymore. And bases, we need protons. We'll do anything to get them. Protons, you can protons away. I'll take some protons. You think that when you get these two together, you'd have some pretty great chemistry. But the truth is, when they're together, they often don't react. Whoa. That is, until water gets involved. Once you have water, acids and bases react. Whoa. Here, take some protons. All your bases belong to us. Here you go. Take some protons. I don't need more. I want more. I want more protons. Here. Water is a solvent, allowing the chemical reactions to take place. Depending on the strength of the acids and bases, that reaction can be mild. Would you like a proton? Oh, no, really. I could. Please take it. Oh, well, thank you. That's very generous. Have another. No, perhaps, maybe I will. Here's one. Okay, maybe just one. But if the acids and bases are strong, the chemical reaction can be really extreme. This is what's going on in the antacid tablet, and why, without water, nothing happens. Oh, water! Water! Come on! What'd you do? What?
That's the last one.
Lisa and I are maxing out our chemical-powered rocket not by making it bigger, but by making more of them. How many more? 400 caps all glued down, 400 antacid tablets, or part of, all glued down, and they're glued on this fancy-pantsy spinning surface. So we rotate this part upside down. We fill each container with a little water and snap it on underneath. This way, the antacid tablet and the water don't mix until we flip it back over. It also allows us time to snap them all on. Okay, ready?
Ready.
All right, 400 containers. Here we go.
Let's do it.
Once we flip the board back over, the reaction started taking place, building up carbon dioxide gas and increasing the pressure until...
What do you think?
Oh, yeah. Oh, yeah.
Oh my goodness!
Good luck if you catch them.
Wow, that one went really high. Oh!
Awesome! That totally was great. Wow. Okay, so high fives on that.
Yep.
That worked spectacularly.
That was awesome.
So we've done this.
Let's go bigger.
Let's go bigger.
Bigger.
Okay. So let's go and we'll clean this
All
up
right.
afterwards.
Yeah,
okay.
let's do it.
Okay, let it go. Whoa. Whoa. This is a balloon, and this is an orange. When you put them together, a chemical reaction happens. How'd you go in there for a minute, didn't I? No? No? All right. Well, you can actually do a chemical reaction between a balloon and an orange. You see, balloons are made of latex, which is a kind of polymer that's very, very stretchy. And orange peels contain a chemical called limonene. Limonene breaks down latex. So, we have 3 questions. The first is, why does this happen? Well, like I said, it's all chemistry. You see, balloons are made of polymers, chains of molecules held together by chemical bonds. A limonene molecule attacks those bonds. Nom nom nom, nom nom nom, nom nom nom, delicious. And breaks it. That separates the polymers, and that pops the balloon. But remember, it only works with natural latex. So make sure you're using natural latex balloons. Second question, why do they call it limonene when it's in orange peels? I mean, yes, it's in lime peels and lemon peels, but the chemical itself smells like oranges. They should call it orangenine or citrus fruitinide or... Anyway, third question, should we max it out? Of course we should, come on. 200 balloons versus 2 bottles of limonene. Ready? Go! first attempt to max out our chemical rocket was 400 plastic containers. Oh yeah. That worked well, but now it's time to make the container larger. Whoa! Giant maxed out chemistry rocket canister. I have a big plastic container with a groovy lid that sits there on airtight, which is great.
And I have a giant jar of antacid.
How many? It was like 60 antacid tablets or something?
At least.
This works exactly the same as our smaller containers. We dump the antacid in, seal the lid airtight, then flip it over. And now would be a good time to mention not to try this at home. Okay. Oh, it's not gonna take long. All right, so that was the canister version. Now we need the pop bottle version, the rocket version.
Yes.
Okay, let's go make that.
Let's do it.
Okay. This is a light stick. It creates light using a chemical reaction. There's a liquid chemical inside and also a glass container that holds another chemical. When you bend the light stick, you break open the container and the two chemicals mix, creating light. There you go, light sticks, chemical reaction. And yes, of course we're gonna max it out. This is a whole bunch of the two chemicals in a light stick. Let's max it out. So how does a chemical reaction produce light? Well, a lot of chemical reactions produce energy. You might think of a chemical reaction producing heat. Well, heat is a kind of energy. This chemical reaction also produces energy, just energy in the form of light. It's just a different kind of energy. Whoa, maxed out light stick! And now for a Science Max quiz. Chemical change or not? What's a chemical change? Well, let's demonstrate. Look at this. It's a happy little molecule of iron. And here's another molecule of oxygen. If they were to have a chemical change, they would react and form different molecules. Look, it's a molecule of rust. Rust is a different chemical than either iron or oxygen. It's a chemical change. Now, if these molecules mixed and did not change, then it's not a chemical change, it's a physical change. Sometimes it's hard to tell if it's a chemical change just by looking, but asking what kind of change it is leads to good science. So let's look at some examples. Vinegar and baking soda. Is it a chemical change? Yes. Vinegar and baking soda react to form different chemicals. Sodium acetate, that's the white stuff that's left over, and carbon dioxide, which makes the bubbles. How about a nucleation fountain with Diet Cola and mints? Haha! A lot of people think that's a chemical change, but it's not. The mints cause carbonation, the bubbles, to escape faster. But in the end, you still have cola and mints, no new chemicals. And without the carbonation, nothing happens. So, it's a physical change. Take a guess at this one. Glow stick chemicals. Well, producing light or heat is usually a sign of a chemical change. How about mixing sugar and water to make a sugar pop? That's a physical change. You start with sugar and water, you mix them, and when you have a sugar pop, what chemicals are you left with? Well, sugar and water. So, no chemical change. It can be hard to tell sometimes, but whenever two things mix, think to yourself if it's a chemical change or a physical change. And now you know it's either one or the other. And that's the first step to good science. Thanks for playing our Science Max quiz. Our maxed out rocket worked great! Now to make it look more like a rocket.
So we have a mesh bag here to put the antacid in.
Right.
And we have some paper clips attached to it.
And what are the paper clips for?
Well, Phil, we have a magnet.
Ah!
And so the magnet sticks to the paper clip.
And so that's what we have here. You see, the bag is full of the antacid tablets, which we put through the mouth of the bottle, and the magnet is holding the paper clips on the other side of the plastic, so we can sort of move it along. So we can start with the bag over here where the water's down there, but now we attach the launcher, like so. All this effort is to keep the reaction from happening until the bottle's on the launcher and we're ready to go. And then, as we pull the bottle over, we bring the bag up this side, And there, the water and the antacid have never touched.
No reaction.
All you need to do now is we pull this magnet away and the bag will fall into the water. And then we will have the launcher down here. And we pull the release and the rocket will go. We add some weight to the launcher to help keep it in place. Okay, right? Wait, glasses.
Safety first.
Okay, ready? And then we pull the string with the magnet. That drops the bag of antacid tablets in the water and starts the chemical reaction. Because we have a latch holding the bottle down, we can wait until the chemical reaction happens fully. And there's a lot of gas pressure in the rocket before...
3,
2, 1.
launch! Woo! That worked.
Yeah, it hit the ceiling. I think we need to do this outside.
Yeah, I think we definitely have to do it outside.
All right, totally great. Weird. Anyway, I was saying we should put 3 or 4 of... 3, 2, 1, go! There it is. Yeah! We tried it outside and it worked great. The only thing left was to max it out even more. So, larger chamber?
Yep, more antacid.
More antacid, more air, more water.
Absolutely.
Bigger rocket. Okay, so you know what? I know how to splice 2 bottles together and we can increase the size of the chamber. This is sodium acetate. How do you get sodium acetate? Well, when you do a vinegar and baking soda reaction, what you have left once the reaction is finished is sodium acetate. It's a crystal, and you can do something fun with it that may seem familiar. You make a supersaturated solution of sodium acetate by heating water and dissolving as much as you can, and then when it cools, you can get the crystals to reform. Now, if you did this with sugar, you could make a sugar pop, which we've done before. If you do it with salt, you could make a salt pop, which is less appealing. And if you do it with sodium acetate, you can do this. Just like with the sugar pop, all it needs is a seed crystal to get the crystals to reform. But unlike sugar, which takes a few days, sodium acetate recrystallizes right because we heated the water, allowed more crystals to dissolve in it. Ooh. Cooled down at crystal hotter than there should be at this temperature. They want to turn back into crystals, and what we need is something. I've colored this one because, I don't know, maybe it'll look cool. A tiny crystal on the end of the stick is all we need to start the reaction. Whoa. Oh, and there you go, sodium acetate. That one wasn't done yet. We've gone from small containers, oh yeah, to a large container, to a rocket. Yeah! So what's next? Super maxed out rocket! 12 2-liter bottles all spliced together to give us a very large chamber to build up pressure with. So the chamber is all the same, so it's all one big hollow tube, and now we're gonna fire it off. Let's go!
Let's do it!
Awesome rocket! Yeah! Lisa and I follow the same procedure as before. We use a bag of antacid tablets held up inside the rocket with a magnet. And once it's sealed on the launcher, we pull it off, let the antacid mix with the water, let the chemical reaction happen for a while to produce enough gas pressure, and then we fire it. Okay, here we go. 3, 2, 1, go!
Oh my God!
That is the highest I think we've ever shot a rocket on Science Max.
That's amazing.
Well done. Chemical reaction rocket. Thank you very much for joining us on Science Max Experiments at Large. We should build another rocket because that one is probably broken.
That's done.
Okay, let's go.
Let's do it.
All right, so this time I think what we should need to do is... Oh no, it's nothing but garbage cans in there. We gotta turn the portal off. Come on, we gotta get... Science antacid, the perfect antacid for all of your science needs. So let's launch some let's launch. See, vinegar is a base and baking soda is an acid. That's not right. Vinegar is an acid and baking soda is a base. Science guy.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max!
Try yours.
What makes airplanes, or basketballs, or people fly? It's air. As well as a bunch of other things that we learn when we try to make a giant paper airplane.
So that didn't work.
All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ha-ha! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide, and open it up. And here's the trickiest part. See how it's bent like that? You push it open like this, and this is called a pocket fold because you wanna make a little pocket and push it up against there. Fold it flat like this. Fold this tip down over there like that. Then fold it around the back side. Then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings and ta-da, the Sky King paper airplane fold. Now, as Science Maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, experiments at large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. Uh-oh, that's never good.
Whoa, Phil, I'm so sorry. You okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents How to Fly Your Paper Airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. Sorry, high pitch.
Great, great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah. Yeah? No. Yeah. Yeah is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Here we go.
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace science and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh, yeah, you're right. The ink doesn't go straight. It follows the wing down.
It follows the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right,
generating
and
lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay.
Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out.
I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Yeah! Okay, be very careful getting off it. Whoa! All right, let's fold it. Nose on that side. Okay.
Remember, we're folding the exact fold we did in the lab, only on a larger scale.
We have a tape malfunction down here.
But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
Okay. There.
Perfect.
Yeah. Giant paper airplane! Ha ha ha!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Whoa. Yep. Maybe.
Like, I'll just.
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah. Go for it.
Okay, here we go. Wow. What do you think?
Oh man.
I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look. Let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very floppy.
Very floppy. What if we supported the plane like we put struts or something in it? Like,
like this stick, if we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like, so
Like
foam
Yeah,
stuff?
and like hollow tubes.
Hollow tubes?
Hollow
Good,
tubes.
good. So we'll put a whole bunch on there, we'll tape them on so that it doesn't flop around.
Yeah.
We'll try it again.
Yeah.
Yeah, I think we got
Yeah.
something.
Okay, great, let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
Put that in there. And then that.
Great, look at that. It's not even flopping around. It stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be. Well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just.
Phil, there's a lot of stuff on here.
There.
But like it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, let's do it. Let's do it. All right.
Okay. All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, yeah, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do, and then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. Hey, Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah.
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up.
And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour. All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour. Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly. Oh, woo! There you go, our Mark III model paper airplane. Now, I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap, but we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose.
We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Okay, all right.
Phil, that was great!
All right! This throw worked best, but I know what you're thinking. Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is
Largest paper airplane I've ever thrown! Woo! Hey, you guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large.
Where were the stairs? Oh, never mind, I found them.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Did that sound like music?
Sounds good.
Stop!
Yeah.
Yeah.
Yeah?
Yeah.
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 Word has lost all meaning.
Science!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha! There are two... Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets,
you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel. See, they don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make a levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate meat. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Guys, ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what has attracted the magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, is definitely attached to the floor. Thank you. All right, now, if I just get this lined up. Oh, look at that. It could totally, oh, wait a minute. Totally, it doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets,
everybody wins because magnets are everywhere. This has been a Science Max quiz. Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science! Turns out trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan. Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws, or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science. So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy. And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear, no, that's okay. I can fix this. If I just maybe, maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, experiments at large, and we'll see you again as soon as we get into the camera. Today, we're gonna be looking at the power of magnets. 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 Wait, okay. This one here is called a neodymium magnet, or a rare earth magnet. It sticks to this magnet. Ramona, the fish fell. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today, I'm maxing out the power of water.
Water is very heavy. Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're going to be looking at water. But water is very heavy. But that's okay, because we need it to be heavy for this experiment to work. I don't know if I need that much of it, though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car. You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom. Trim them down, maybe about that much. Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and do the same thing on the other 3 sides. Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base. Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside. And don't forget your safety glasses. Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it, and kink the straw, and woohoo! Woohoo! Haha, there you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
okay.
Today, I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda, and you pressurize this container,
And the water shoots out that way. So the car goes this way.
Ah, Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your stuff. This is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole and weld them on. I don't know if that's...
Something tells me this wouldn't work. So
okay,
we need,
sure. I got some other stuff over there maybe that we could use.
Check this out. Yeah, I think this would work. This would work a lot better.
Well, this is my stand-up wash tub base.
Your what?
So we'll reuse it. Yeah?
Okay, you know what I'm thinking now, though? I know this... The problem is, I think this is like an oil drum, right?
It is. It's an oil tank from a house.
And these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower
That
or
makes,
something like that.
So all we need to do is get a pressurized water tank.
Okay.
Put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All right.
Let's get to it, man. Okay.
I got some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me. So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we go.
So I've joined Anthony and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way.
Okay. Ha-ha! So, water car, maxed out version.
Huge.
Water tank.
And filled with lots of water and lots of air. Too. Yeah, pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
no, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it, okay.
Okay, here we go. 3,
2,
1,
go!
We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome.
That was a great run, yeah.
That's amazing.
So pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So.
Because then it would be too heavy, right?
Exactly,
Much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water,
Okay.
and then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water.
Right.
And I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah. All right. Amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out. The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of? Power washer pumpkin carving! The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home. Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did someone say Overwhelmo?
No, wait, no. Next. No, not that. Okay, good. Okay.
Behold, it is I, Overwhelmo!
Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy.
A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic!
Yes? Is that it?
Yes?
Well, it's not magic.
It is defying gravity.
Nope.
The water would fall and the card would fall to the floor.
It's not magic.
This is magic.
No, it's science.
Horse feathers.
Look, the reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up.
Balderdash!
All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles?
Yes.
That's bad news. Science, not magic.
Well, I will return, and then you will see your mind will be melted by the... No, that's not my music. Hold on. You will rue the day when... That's not my... Hold on. Overwhelmo shall return!
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car! So this is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump. That's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump and we're ready to go.
So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah.
Nothing happened.
No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way. That's good.
And then we'll need, I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it, I guess we aim it
Down at the, yeah, exactly.
like that.
And then
At the paddle wheel, and then the paddle wheel spins, and that propels the car.
Exactly.
Right?
Right.
Okay.
Okay, well,
We can do that. Let's do it.
sounds good,
Put
yeah.
it together. You know what? I have a paddle wheel because I had a failed hydroelectric.
This is called flyboarding. Wow. Powerful jets of water are being shot out from this board at my feet. Whoa.
The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well,
We don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform. Woo-hoo!
flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it.
It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo!
Our maxed out water car didn't work so well. The main reason is that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go.
Okay, so here's the latest version of the water car, water wheel.
Yeah.
All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan.
Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it. And Phil, yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to.
Even half full, you
Even
can't
half full,
move
I
it.
think we need less fuel. We're gonna get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never.
Okay.
It never moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go in its own.
Exactly.
Okay.
Wanna get
Yeah.
down?
Absolutely. Let's do it.
We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference. The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going. All right.
Amazing! Yeah! Look at it, man. This thing worked like a beauty.
It worked all. It went all the way. Way to go. The water car, finally a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely.
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.
Let it go and.
There we go. Oh, careful.
I can't really see with my goggles.
Behold the power of physics. Yeah.
The door's full.
This is called foot. Whoa! All we have to do is wait.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max!
Science.
Today's Science Max is all about balance.
Okay.
If it's a potato or if it's me, figuring out how things balance is what we're all about.
It works really well.
Swinging, spinning, and staying put. Today on Science Max Experiments at Large.
Greetings, Science Maximites. Today, we're going to be talking about balance, or what you call balance in science, which is center of gravity. Now, the center of gravity is a place you can find in any object where it's equally balanced on all sides. I balanced this spoon on the eraser of this pencil, and where the spoon is balancing is its center of gravity. But if I take this little tiny dime and put it in the spoon, it doesn't balance anymore. But if I put the dime in this spoon and balance it in a different spot, I can find the new center of gravity, and the spoon balances again. Here's another experiment you can do. Take a potato and a ruler or a stick. Try to balance the potato on the ruler. I'm gonna save us both a lot of time. It's really hard to do. The potato does have a center of gravity, but because of its shape, it's going to be really hard to find and really hard to balance. But if you take some forks and you stick them into the potato, you're no longer just trying to balance the potato, you have to balance the forks and the potato. And it gives it a very different center of gravity, which makes it a little bit easier to find and a little bit easier to balance. Ha ha!
Let's take a closer look at how the center of gravity works. Using our potato. No, that's too close. Back off a little bit. Okay, good. If you want to find where the center of gravity is, you can hang an object and draw a line straight down. Then hang it from a different spot and draw another line. Do this 1 or 2 more times and you can see where the lines meet is the center of gravity. If our potato was balanced on a stick, the center of gravity is a long way from the stick, so it's going to be pretty hard to balance. Now, let's stick some forks in the potato and try again. One line there, and a line there,
And you can see that the lines all come together down here. That's right, the center of gravity doesn't have to be on the object. With the center of gravity way down there, when we try to balance the potato and the forks on the stick, you can see the center of gravity is much closer to the stick. That makes it way easier to balance.
Now, because you're science maximites, I'm sure you know that a potato and forks is just the beginning. Everything you have in your house has a center of gravity, which means theoretically you can balance anything. Try it yourself. Find things around the house and see if you can get them to balance. And if you can't, try adding things to increase the center of gravity and make it a little bit easier. Now we're gonna max it out. That's why I'm gonna go to the center for skills development and training, and we're gonna explore center of gravity even more. See if we can get something to balance. And what better thing to balance than me? Oh, table, right. Hey, this is Sandhya and Swapna. No, Sandhya and Swapna.
Right.
And they are going for their PhDs in science. And you guys, thank you for coming.
Thank you.
Work with Let's Talk Science, right?
That's right.
All about science education, just like us. And I'm glad you guys are here because I need to max out this. Oh, look at it balance. Whoa. Hey, whoa. Okay, I got it. It's fine.
Good. So we're gonna get a gigantic potato?
No, I thought we would use me instead.
So you're the potato?
Yeah, I guess I'm the potato. All right. And I need something to balance on.
Well, how about a tightrope?
Oh, yeah, a tightrope. Have either of you done a tightrope before?
Nope.
Me neither. All right, let's set one up.
All right.
Okay, good. Yeah, I guess you're right.
We're gonna take our balancing potato experiment and max it out. To get a potato to balance is pretty hard, but if you stick forks in the potato, it works a lot better. In our maxed out version, we're gonna balance on a slack line, which is sort of like a tightrope. It's a flat strap tightened between 2 points. And in this version, I'm the potato. And instead of sticking giant forks in me, which is not something I want to try, Sandhya, Swapna, and I are going to experiment to see what I can do to improve my balance.